Differentials. The objective in this lesson is to find the differential of a function and use it to approximate changes in measurements. Recall that for a differentiable function, y equals f of x, the derivative can be defined as dy dx, which equals f prime of x, which equals the limit as the change in x goes to 0 of the change in y divided by the change of x, which also can be represented as the limit as the change in x goes to 0 of f of x plus delta x minus f of x, that's the change in y, divided by delta x, the change in x. The change in y divided by the change of x can be approximated by f prime of x when the change in x is extremely small, close to 0, but not equal to 0. This leads us to solving this equation for delta y by multiplying both sides by delta x, that the change in y, delta y, is approximately f prime of x times the change in x, when that change in x is very close to 0, but not equal to 0. This leads us to differentials. Let y equal f of x be a differentiable function, and let delta x denote a change in x. The differential of x, denoted dx, is defined as dx equals delta x, which does not equal 0. There is some amount of change in x. The differential of y, denoted dy, is defined as dy equal to f prime of x dx. Now let's take a look at a function y that is called f of x, y equal f of x. If we take the derivative of y with respect to x, dy dx, that equals f prime of x. And if we solve for dy by multiplying both sides by dx, we get that dy equals f prime of x dx. dy being the differential of y and dx being the differential of x. That's just what this is. dy equals f prime of x dx. Let's take a look at this graphically. Here we have a function, y equals f of x, and a tangent line to this function at the point P. So the point P corresponds to a certain x value, which then also corresponds to a certain y value. We'll call that y value f of x, the function evaluated at that x value. Now if we change x a certain amount, let's call that change in x delta x, that takes us to another x value. We'll call that x plus delta x. That value on the function would be approximately right there, and the corresponding y value would be noted as f of x plus delta x, the x value plugged into our function f. Now from f of x to f of x plus delta x, that gives us a certain amount of change in y. Now we often use tangent lines to help us approximate function values, so that x plus delta x on the tangent line corresponds to that y value right there. So we've got the difference between the y value at x and the y value approximated on our tangent line, and that's going to be called the differential of y, dy. So we've got delta y, which equals the change in height of the original graph of f from x to x plus delta x. That's that change in y. And then we've got dy, the differential of y, which equals the change in height of the tangent line to f from x plus delta x. So it's important that we remember that dy, the change in y of the tangent line, is approximately equal to delta y, the change in y of the original function, and that's when our change in x is very, very small. So correspondingly, dx, the change in x of the tangent line, equals delta x, the change in x of the original function. So again, the change in y, which is approximately the differential of y dy, equals f prime of x dx. The change in y of the function is approximately equal to f prime of x dx when dx is small, when the change in x is small. Let's take a look at some examples. 1. Find the differential dy of the function y equals x times sine x. Now I notice this is a product, x multiplied to sine x, two functions with variables that are multiplied, so I'm going to think of using my product rule, fg prime plus f prime g. dy, my differential of y, equals f prime of x dx. I'm going to start with just simply stating that. Now I'm going to find my derivative of this using my product rule. So dy equals f times g prime cosine x plus f prime, which is 1, times g, which is sine x, and it needs to be multiplied by dx, but it's not just sine x that's multiplied by dx, it's all of f prime of x. So I make sure to use my parentheses to show that it's all of it multiplied to dx. Two, use differentials to approximate the change in y equals x to the fourth. So first of all, we remember that the change in y can be approximated by the differential of y, which equals f prime of x times dx. Our derivative of x to the fourth is 4x cubed, so dy is equal to 4x cubed times dx. Let's apply that as x changes from 2 to 2.01. So if x changes from 2, that means x starts as 2. And if it changes to 2.01, then 0.01 has been added to 2. So that means my change in x, or differential of x, dx, equals 0.01. Now I plug those in to what dy is. So I have dy equals 4. Instead of x cubed, it's 2 cubed. Instead of dx, it's the value of dx, 0.01. I compute that, which is 4 times 8 times 0.01, and that makes 0.32. So the change in y is approximately 0.32 as x changes from 2 to 2.01. In part B, we're looking as x changes from 3, so that means our original x value is 3, down to 2.998. So this time it went down of a change instead of up in change. So that means my change in x, dx, equals negative, and the difference between those values, 0.002. So we remember that dy equals 4x cubed dx, and then I can plug in those values from this particular problem. 4 times 3 cubed times negative 0.002, and that value comes out to be negative 0.216. Negative 0.216. The approximate change in y is a decrease of 0.216 as x changes from 3 to 2.998. Let's add those words to these answers. So this shows that y increases by 0.32 as x changes from 2 to 2.01, and this shows that y decreases by 0.216 as x changes from 3 to 2.998.